Hello, my name is Jamie Tucker-Foltz from Harvard University. I'm presenting joint work with Richard Zeckhauser on playing the divide and choose game given uncertain preferences. This is the online version of our EC 2023 conference presentation. The full version of the paper can be found on arXiv. Our work takes a new look at a very old mechanism, namely the divide and choose allocation mechanism. How old? Well, it actually appears all the way back in the Bible when Abraham and Lot have to divide the land of Canaan, with Abraham cutting the land into two pieces and letting Lot choose which piece he wants to take for himself. Today, it's used to divide inheritances among children, to dissolving partnerships via buy-sell contracts. It's a very widely used system. It's very simple. Player one, who we call the divider, cuts the resource into two pieces, and player two, the chooser, decides which player gets which piece. There's a vast literature in computer science and economics on this mechanism and its variants, and they're usually studied from the perspective of satisfying axiomatic fairness criteria, such as envy freeness, proportionality, etc. And there are some strategic considerations, but it's usually in the context of, we want to make sure that it's how do we do a fair division without having even in the context of strategic behavior. Our paper takes a new look, which is actually suppose that you have a prior about the other player's preferences. How should you optimally play this game? And this is a question that has not really been asked before, except in a few cases where there is no uncertainty at all. So our paper is really about the case when preferences are unknown. So just to briefly introduce some notation to talk about our model, we consider n divisible goods, numbered 1 through n. Each good is homogeneous and divisible. So you can think of this, if you're in a cake cutting model, for example, as n separate cakes. You always have the same value for every piece within this good, and it's divisible. So it's a two-stage game. The divider partitions the goods into pile 1 and pile 2. And remember, it's divisible, so you can put 0.6 of a good in pile 1 and 0.4 of a good in pile 2, for example. And then the chooser determines who gets which pile. And we're going to adopt the convention that pile 1 will always be the pile that the divider is going to be more happy if the divider gets. Both players have additive risk neutral preferences. We're going to write the GDI to be the divider's value for each good I, and GCI to be the chooser's value for each good I. And we're going to assume that there's common priors on these values, which are independent across goods. Okay, so let's just get into it with a little warm-up example. Here, there's no uncertainty. We're going to introduce that next. We have three goods, and it's common knowledge that the values of these goods are 4, 7, and 3 for the divider, and 3, 5, and 2 for the chooser. So you're the divider. These are your goods. What is the optimal division? Well, if you think about this enough, you will eventually realize that the optimal division is to put all of good 3 and just less than 0.6 of good 2 into the preferred pile 1, leaving the remains in pile 2. Okay, and you can make epsilon equal 0 with the right equilibrium concept. The chooser will break indifference in favor of the divider. So why is this optimal division? Well, here's the algorithm that you can use to find it. We're going to define the critical ratio of good I to be the ratio of the divider's value of the good to the chooser's value of the good. And we're going to start with all the goods in pile 2. So when the chooser is going to take pile 2, the divider gets nothing. And then we're going to pull things out into pile 1 in descending order of critical ratios. So we first see that good 3 has the highest critical ratio. It's worth the most to the divider relative to the chooser. So we're going to take all of good 3 and put it into pile 1. And then we're going to start taking part of good 2 into pile 1, but we're going to stop at the point where the chooser is indifferent because we want the choosers to still pick pile 2. And that gives you the optimal allocation. And this is a visualization of this. I'm taking an entire mass of 1 of good 3 into pile 1 and 0.6 of good 2 into pile 1. This is how we're going to visualize these divisions. And so it's not hard to prove that this is the optimal algorithm to handle the case when the divider knows the chooser's values. But what happens when there's uncertainty? What does the divider do? Does the strategy still look similar? What twists arise? What do optimal divisions look like? How can the divider compute them? How should the divider split goods fractionally between the two piles? In that previous example, we saw that only one good needs to be split between the two piles, and it's because that's the point where the chooser is indifferent, and you only move one at a time. But is this true when there's uncertainty over the chooser's value? Finally, is it better to be the divider or chooser? This is a very interesting question. And we're going to provide some answers about when's better to be the divider, when's better to be the chooser. So here's an initial example to show some of the weird things that happen with uncertainty that don't happen when the divider knows the chooser's values for each of the goods. So in this example, we have 6 goods. The first 5 goods are all worth about 100 to the divider, and the last good is worth 200 to the divider. And every good, if the chooser's value for each good is drawn independently from a normal distribution with mean 10 and variance 1. And this is just a plot of the PDF of this normal distribution. You're the divider, you see your own values, you don't know what the chooser's values are, but you know this prior for the chooser's values. Now what should the divider do? So you might think to adopt the same sort of strategy. We start with all goods in pile 2, and the divider is going to get none of them, probably. And then we take the highest value good, which is good 6, and place that entirely in pile 1. And then maybe we start taking we start taking the other goods in order. We first transfer all of good 5 slowly into pile 1, and we see that's still very likely that the chooser is going to pick pile 2. And so we're happy with that. And we just keep taking one good at a time until we reach the point where my expected utility is going to be less. Where my expected utility starts to decrease because of the high probability the chooser picks pile 1. So you would think that that might be optimal, and certainly we initially thought this, but in fact, that's not the optimal division because all but one good are divided. In this algorithm, only one good needs to be fractionally allocated between the 2 piles, and in fact, this is the optimal division. And I will explain how we compute that on the next slide. But all the goods need to be fractionally divided to get the optimal utility for the divider, except for the good 6. So why does this happen? Why is more than one good split? This doesn't happen in the case of known preferences. And so here's a little sketch of the reasoning why this happens, is that if the divider is doing a good job, the chooser's mean for pile 2 should be higher, right? If they don't do this, then it means that the chooser is more likely to pick pile 1, which is going to be bad for the divider because we're adopting the convention that pile 1 is the one the divider wants to pick, wants for himself. And because the mean for pile 2 should be higher, variability in the pile's values is bad. It's better for the mean to be for the values to be concentrated around the mean, so that it's more likely that the chooser picks pile 2. So given that variability is bad, it's good to diversify by making it more likely the chooser they'll make it more likely the chooser picks pile 2, because if you have goods that are fractionally allocated, it's like spreading your it's like diversifying into many different things. You're not placing all your eggs in one basket. You could get extreme values. This kind of minimizes the impact of variance in the chooser's values, and so it makes it more predictable, therefore makes it more likely to pick pile 2. So this is a principle that applies in this uncertainty case that does no analog in the case where preferences are known, and it makes things really challenging. In particular, it's not remotely clear how you would go about solving this computational problem that the divider has, where they have the input to this problem is their value for each good and some description of the chooser's prior for each good, and they have to compute an optimal division. How do they reason about this? How can we do this with some sort of algorithm? And so I want to tell you about how we go about solving this problem in the paper in some special cases. So I'm going to define an auxiliary variable qi, which is going to define the division for each good I. It's the amount of good I in pile 1 minus the amount of good I in pile 2. And so this is going to range from -1 to 1. And we're going to call capital P the probability the chooser picks pile 1, which, if the divider is doing a good job, should always be at most 1/2 because they prefer pile 1. And so if using these variables, we can compute the expected utility of the divider given QIs, which induce some capital P, and it's this expression where, and I'm not going to go through the details of how we do this derivation, but the point is we can do some simple manipulations and get it into the following form. And what do I like about this following expression? The expected utility of the divider is equal to the sum of 2 things. The first term here is just half the value of the sum of all the goods to the divider. This has no bearing on the divider's optimization problem. It won't change. The only variables the divider gets to manipulate are the q's, which determine the p as well. The second term has 2 parts. and they represent a fundamental trade-off the divider has. If you make the QIs larger, that corresponds to transferring more value into pile 1, which is going to increase the value of this term. However, it also decreases the value of this term because it increases the probability P that the chooser picks pile 1. So we have to trade off these two terms that are multiplied together. And the key insight of our algorithm is that we can try many different values of P and just like guess, well, I think this might be the optimal value of P, and hopefully one of them is close to the true optimal value of P. And with respect to that, then we optimize over the Q variables subject to the constraint that the chooser's probability of picking pile 1 is going to be less than or equal to P. And in our paper, we show that if the priors are normal, then it turns out that this becomes a convex quadratic program, so we can solve it in polynomial time. Moreover, if you miss the optimal P by a small amount, you still recover a 1 minus epsilon fraction of utility for some polynomial function of delta. And what this implies is that we have an algorithm that's a fully polynomial time approximation scheme for the case when chooser values are normally distributed. And this is just an example to show that we really do need to guess many different values of P. We can't optimize P in a more if we were able to optimize P, say, with a binary search, then we could get not just a fully polynomial time approximation scheme, but also a stronger guarantee that we can exactly solve the decision problem of determining whether the value is greater than some amount. And but we can't do that because, as we see here in this graph, this is just a cooked up example to make this interesting graph here. On the x-axis, I'm placing the values of P that we're going to try to guess. And on the y-axis is the optimal divider utility, given that the constraint that the chooser picks pile 1 with probability at most P. And so as we can see, there's multiple local optima, even for only 4 goods here. We have 4 possible local optima, so we really do need to have a fine mesh of different P values to try to be able to find this peak. Okay, so I promised you we're going to talk about whether it's better to be the divider or the chooser. And I think this is a really good toy-specific problem to ask this question in. So you're given, say you're given 50 goods, and you know that each good is going to be uniformly, the value of each player for each good is going to be independently drawn uniformly from 0 to 1. So this is 100 IID random variables here. As the divider, you know your own values. As a chooser, you know your own values when you're playing this game. But I'm asking you, before we even begin that, without knowing what your values are, originally, do you want to be the divider or chooser? Once you make the choice, then you get to see what your values are. So this is a fun problem to think about. And you can pause this recording here if you want to think about it. I usually, when I present this in person, I ask people to raise their hands. And people more often than not get this question wrong. So pause here. Okay. Or maybe you didn't pause. Anyway, if you thought about it at all. Now think about the same question if there's only 2 goods. Does your answer change at all? I'll let you think about that one for a moment now. Okay, so is it better to be the divider or chooser? Well, it turns out the answer is that with 50 goods, it's better to be the divider, and with 2 goods, it's better to be the chooser. And this is a more general phenomenon that we prove in the paper, that for as long as we have a distribution that is like uniform distribution from 0 to 1. In other words, it has to be bounded and also bounded away from 0 in a certain sense. That for 2 goods, the chooser is strictly better off, and for all sufficiently large n, the divider is strictly better off. Okay, and here's the exact values in this case with uniform distributions. In the case of n equals 2, and I'm in this table is the expected utility per good. So the baseline is that you can always divide all goods evenly and expect that you're going to get half of your average per good, which is going to be half of half. So if you divide evenly and then choose randomly, essentially, that you can always get this utility guarantee of 0.25 per good in this setting. And it turns out in the limiting case, that is the chooser's utility. So the reason this is the case is that the divider basically takes their highest value goods and places them at their highest half of their goods and places them in pile 1, and their lowest half of the goods their lowest value is half of the goods and place them in pile 2. Then they just make pile 2 have slightly more goods than pile 1. And if they do that, they're essentially getting the top half of their distribution. So the divider is going to have an expected utility of 3/8. That's what this 0.375 is, because they're getting, they're going to get half the goods, and each good is going to be, in the limiting case, it's going to have value drawn uniformly between a half and 1. So their average value for each of the good they're going to get is 0.75. So the divider is getting essentially their best half of their goods, and the chooser is getting a random half of the goods. And so that's why the divider does better than the chooser in the limiting case. The n=2 case is actually it's kind of the harder case to understand. I'm not going to go through that. You can see the details in the paper why the chooser is always better off. But in the uniform case, I will say this is a hard problem. These are difficult numbers to compute. The utilities here are exact in the limited case. The utilities for the n=2 case, turns out that we can solve this because it's small. This number 0.264 is an approximation of the fraction 19/72, and the chooser's utility is even nastier. It's this gigantic expression. This is a very hard problem to solve. And this is a plot just to show that this phenomenon holds for other distributions besides uniform distributions. Here we have a normal distribution, and I'm plotting the number of goods on the x-axis and the expected utility per good on the y-axis. So this is the divider's utility. This is the chooser's utility, starts higher than the divider and then eventually crosses over around 13 goods. And then the divider's utility does the opposite. Okay, so just to wrap up and recall the main messages of this paper is that uncertainty fundamentally changes the game. Here's just a list of all the things that are true in the case of known preferences, but are false in the case when the divider does not know the chooser's values for the goods. The outcome is always proportional. That's an obvious one. Sometimes the chooser will pick pile 1, and then the divider will end up with less than half of their value. At equilibrium, at most, one good is split between the piles. This is, as we saw, this is true with certainty, but it's very false with even some simple examples of uncertainty. Optimal divisions can be found by a simple polynomial time algorithm. We do have an FP-toss for some special cases, but the general problem is very intractable. Optimal divisions are monotone and critical ratios. This is another property that you can back out of this simple algorithm in the certainty case, and I didn't show it here, but there's examples in the paper showing that this is false with uncertainty. And this one's actually even more bizarre, which again I didn't have time to show in this presentation, but it's in the paper, which is that you can beat your baseline utility, your proportionality guarantee, if only if the critical ratios of all goods are not all identical. This is true in the certainty case, not true when preferences are unknown. And finally, divider is always better off. That's another observation you can see. And when the divider knows the chooser's preferences, they're able to extract basically all of the surplus possible. And that's not true, as we saw with the small number of goods. There's more things in our paper as well, where we consider the computational problem with discrete priors, and we even allow correlation. We also have a section on risk aversion, where we show how that would affect the game and prove a straightforward result about that. We also consider an extension where the divider can make multiple offers to the chooser in addition to the division, and counterintuitively show this can actually decrease the chooser's expected utility. In some subsequent work that's not in the paper but will be in forthcoming versions, that we were able to extend this FP-toss algorithm to a broader class of distributions. Specifically, we think we can get a randomized polynomial time approximation scheme for when in the special case where the chooser's priors are uniform on intervals. That's all. Oh, and finally, we have experimental collaboration with James Cox and Vyoltsa Sadirai at Georgia State University, where we're going to take lab subjects and have them play a similar game as captured by our model and see how things actually play out. And I'm very excited about that work, so stay tuned for that. So I'll end there, and thank you for listening. I hope I've taught you how to play this game. It's quite fun. You, as the divider, just have to make sure the chooser picks pile 2 and you get the most value you can in pile 1. Thank you for listening.